Hi, everyone. I'm Tali, and today I'm going to talk about layered neural atlases for consistent video editing. Can you hear me and see me? Just a second, I'm organizing the presentation. Sorry, it never goes smoothly. All right. So from the beginning, hi. So today I'm going to talk about layered neural atlases for consistent video editing. And just for context, recently I've been quite interested in analyzing and re-rendering everyday videos. The motivation was really my own personal video collection. You can see a small sample of it here. Most of these videos are of my children, and I take many of these videos, but I hardly watch them because even for me, they could get quite boring. And I was looking for ways to make everyday videos much more fun, artistic, and engaging. And more generally, I'm interested in enhancing the way we can perceive our dynamic world through everyday videos. So just as an example, we may take this video of a child biking and artistically stylize the background in a consistent manner, as you can see here. Or we can take this video of a jumping horse and create a panoramic stroboscopic version of it. And you can see that the horse is being duplicated, but also the shadows that it casts on the ground. Another useful effect would be to just remove objects from the video, like you can see in the example here. So we removed all the people along with the complex deformations that they generate in the scene, and except from one person. So let's think for a second, what is required to produce all these editing effects that I showed you? Obviously, we need to segment out the objects in the video, and actually computer vision has become really good at segmenting objects. But this is not enough. If we take these segmentation masks and plug them into a state-of-the-art object removal algorithm, this is the result we get. So we remove the people, but we didn't remove the deformation of the trampoline. And in order to get a realistic result, we must take into account these scene effects. So video editing really poses this nice challenge. How can we associate objects with their scene effects in the video? Another major challenge is having an easy and intuitive way to consistently edit the video across time. So a video is just a huge volume of frames, and it's a question how can we let the user to naturally interact with this huge volume of frames and to apply edits consistently across the entire video. So I've been addressing these challenges in the past couple of years. At the heart of all this method is a decomposition of the video into layers. So for example, in OmniMat, the setup is as follows. We take the input video along with rough object masks of the object of interest, which we can get using any off-the-shelf object segmenter. And our method outputs a corresponding layer for each of the objects. And as you can see, a key property of those layers is that it doesn't contain only the object, but also all the scene elements that are related to them, like shadows. So this work really focused on the first challenge of associating objects with their effects in the video. But here, the layers are computed for each frame independently. So in this case, we cannot easily propagate information across time. So today, in the time that I've left, I'm going to tell you about a new work that addresses both challenges and allows for intuitive video editing with minimal effort. And this is a joint work with Yoni Kasten, Dolevo Free, and Oliver Wang. So we are still interested in decomposing the video into layers. But instead of having per frame layers, the key idea here is to decompose the video into global unified atlas layers. So as you can see here, we have one layer that represents the entire background of the video, and it looks like kind of like a panoramic image of the background. and another foreground layer that represent the moving objects in the video. Now, each of the video pixels is mapped onto these 2D atlases, and this provides us with a unified representation of the video in the 2D domain. Now, if we want to edit the video, we can do so very easily just by directly editing the atlas images, and then use the mapping to map them back onto the original video. So the task of video editing is reduced to editing these 2D images, which is very simple. But of course, estimating and learning the mappings and the atlases is challenging. We are given only the input video without any labels, without any supervision. And our goal is to learn those atlases and the mapping of the pixels onto these atlases. So where can we get supervision? One powerful supervision signals that we have for free is a reconstruction loss. So we want to be able to reconstruct the original video from this representation, from the mapping and the atlases. So I'm going to tell you a bit in more details about how it works. Okay, so we're given an input video, and now each pixel position, x, y, t, is first mapped into a 2D location in each atlas. And this is done by having two MLP mapping networks that takes the pixel location as input and outputs a 2D coordinate in the atlas space. So those UVs notations that you see here are just 2D coordinates between -1 and 1. And the predicted 2D coordinates are then fed into an atlas network that outputs the RGB colors in the corresponding UV locations. So what I'm visualizing here is basically a discretized image rendering of these continuous atlases that are represented by those MLPs. Each video position is also fed into an alpha MLP that produces an opacity value. This opacity value basically tells us at this pixel position how much is observed from the background versus the background, the foreground versus the background. So now with all these entities, what we can do, we can simply reconstruct the color at that pixel position P by using simple alpha blending. And this essentially allows us to reconstruct the original video and to train this system end-to-end using L2 reconstruction loss, along with some regularizations. So recall that the end goal here is to get atlases and layers that we can edit and interpret. And the reconstruction loss alone cannot achieve that. So we have additional loss terms, which allows us to achieve that. And I'm gonna briefly describe each one of them. So as I mentioned, our main driving loss is a reconstruction loss. We want to be able to reconstruct the original video content from the atlases and mapping. And we achieve that using just a simple L2 loss between the original video colors and the one we reconstruct through the representation. The second term is a rigidity loss. We want to get interpretable, editable atlases. So we want the atlases to preserve the structure of the objects in the original video as much as possible. So to achieve that, we encourage the mapping between the video pixels to the atlas to be locally rigid. Without this loss, you can see that we get distorted atlases, and somehow they all collapse into these small regions within the continuous atlas space. And this is not something that we can use for editing. So the second term is based on optical flow. Recall that what we have here is a pure 2D representation of the video. We don't have any 3D information, but ideally, what we would like to have is that each point in the atlas will correspond to a physical point in the world. So in order to achieve that without having any 3D information, we leverage optical flow. So we compute optical flow using off-the-shelf technique. And then what we want to encourage corresponding points, different frames, to be mapped to the same atlas point. So without this loss, it is surprising, but as you can see here, we are still able to nicely decompose the foreground and background, but the atlas do contain some distortions, as you can see in the zoomed in region here. The optical flow loss prevents that. But unfortunately, optical flow is prone to errors, and when we have occlusions, we don't have optical flows in those regions, and that might create duplications in the atlas. So finally, we have an additional sparsity loss that prevents duplication in the atlas by encouraging kind of like a minimal representation from the atlas. And you can see that without this loss here, we get 2 instances of the motorbike before and after the occlusions. And this, again, will be hard to edit because we'll have to consistently edit both the duplications of this motorbike to get a consistent result. So the sparsity loss prevents that. And with our full objective, we get clean, minimal atlases that preserve the original structure and we can use for editing. We also have an initialization stage where in this stage, we basically initialize the alpha network by encouraging the alpha values to match some rough user masks, like you can see here. We turn off this loss after several epochs, and the network refines this initial masks automatically. Okay, so let's see some results. So here you can see the input video. There is some substantial camera motion here. For example, panoramic stitching will be hard in this case. You can see here the foreground and background atlases. And as you can see, the car is a bit distorted, but we can still interpret it and edit it easily. And what I'm visualizing here is the reconstructed video and also some texture that is mapped onto the foreground object. Also notice how nicely the shadow beneath the car is nicely captured in the foreground atlas. Here is even a more challenging example where we have severe parallax, lots of occlusions, non-rigid motions. You can see the foreground and background atlas. Our method still nicely decomposes the video into these layers, and it is able to correctly track the dog. And now some editing results. So as I mentioned, once we have the mapping and the atlases, we can render the atlas into a discrete image and simply just apply any off-the-shelf stylization technique or filtering technique that we want onto the atlas. So here, for example, I just applied a Photoshop filter onto the swan and mapped it back to the video frames. And you can see how the edit is also nicely captured in the reflection of the swan in the water. Here is an example where it's more kind of like freestyle type of editing, where you can just add some objects like this semi-transparent pink line and the stars onto the onto this white region in the water. And then mapping it back to the video frames will result in this video. And you can see how the stars are nicely deformed and flattened into the water correctly. We can also completely change the background scene by just replacing it with another image that is roughly aligned with the background atlas. And then we can, plug in this boat into a completely different scene. We can also remove objects from the video by not rendering they layer, like in this example here. And you can see that the background is nicely painted behind the car. Or in this example. Of course, because we have these rigidity constraints, it will be very difficult to represent complex geometry, self-occlusions, extreme deformation with just one layer. In such cases, like what you see in the video here, you can see that the foreground atlas does not reliably contain all the body parts of the person that is jumping. But the decomposition is still valid, and also the predicted alpha, you can see it captures nicely the shadow of the person. So this result is still useful. We can still edit it. We can add graffiti on the ground or this yellow spray on the wall, and we will still get a nice edited, consistent video, even in this challenging case. Okay, so with that, I'd like to end. Thank you all.
Tali, thank you. Great talk. And we have a few questions. The first one, how is the 3D non-rigid foreground object represented as a 2D image?
Yes. So you can think about it as kind of like a canonical 2D image that represents the foreground object, and then each pixel from each frame onto this object is mapped onto this 2D image. People from graphics community can think about it as kind of like simply a texture map of the person, just without having the 3D mesh behind the scene.
Okay, another question. Is the background atlas time dependent? Is it a video or an image?
Great question. So the background atlas is actually a static 2D representation of the entire background. So it is indeed a sort of a limitation. So if there are like severe lighting changes in the scene, we won't be able to capture it. Like the alpha channel will have to compensate for that somehow. Extending the atlases to be a video or time varying atlases is a really interesting future direction of this work.
Okay, and indeed we have a couple of more questions and have time. So what are the future directions in your view of this work?
Yeah, so as I just mentioned, including time varying effects such as reflections and lighting changes into these atlases is, I think, will be very useful and interesting. Also, again, here we did everything in 2D because estimating 3D for these types of unconstrained video is really challenging. But I think now that we have a much better understanding how to do it in 2D, perhaps we can take it a step forward and think of estimating full 3D geometry of dynamic scenes.
Okay. And the last one, do you think it would be possible to see this technology in a product soon, for example, in Adobe After Effects?
Yeah, so I think I mentioned it in the talk. The system is trained from scratch for each video. So currently, each video requires a long training time. Which is, I guess, that will be the main bottleneck in really shipping it into a real technology. But recently, we are seeing really remarkable progress in training MLP's type of a representation and nerve-like representation very efficiently. So when I started working on this, I thought there is no chance this could be delivered. But now with all these advances, I think it should be possible.